Hi everyone, we're going to talk about multiplying matrices today. So we talked about how to add and subtract them. Multiplying is a little bit different. So to multiply a matrix A by a matrix B, what needs to happen is the number of columns of A must be equal to the number of rows of B. So columns of A, rows of B. Then the product will have the same number of rows of A and columns of B. Okay, what does all that mean? Well, here's what it means. So suppose you're multiplying A times B, matrix A times matrix B. What we do is we write down the dimensions of A and we write down the dimensions of B. Now, the inner numbers have to be equal to each other. If they're not equal to each other, we can't even multiply the matrices. So to multiply, the inner numbers must be equal to each other. Once they are equal, you multiply them, and the final product matrix will have the dimensions of the outer numbers 3 by 4. Okay? So for example, suppose one matrix is a 2 by 3. Another matrix is a 3 by 3. Can I multiply these? Well, these are the same, so yes, I can multiply them. And what will the resulting matrix be? It'll be a 2 by 3. All right? As opposed to, suppose a matrix is a 3 by 4, and I want to multiply it by another 3 by 4. They have the same dimensions, but the inner numbers are not the same, so these cannot be multiplied. Okay? Now, multiplying works like this. So suppose you're multiplying an m by n matrix, all right? So the way it works is the following. You first figure out what dimensions of your matrix are going to have, and you write down the matrix with that many dimensions, with those same dimensions. Now, suppose I'm going to work on that first entry, okay? Row 1, column 1. What I do is I multiply each element in row 1 with each element in column 1. Suppose I want to find the element here, row 2, column 1. What I do is I multiply row 2 with column 1, row 2 with column 1. All right, so here's another example. Let's say you want in the product matrix C, you want the term 1, 1. You take row A1 and column B1, and we add the products of their respective terms. So if I want to find the term C32, I take row A3, column B2, right? 3, 2, 3, 2, and add the products of their respective terms. All right, so let's do one. So this is a 2 by 3, and this is a 3 by 2. Okay? The inner numbers are the same, therefore the matrices can be multiplied, and my product is gonna be a 2 by 2. So in here, I'm gonna have 2 rows, 2 columns. All right? So suppose now I want to find this number. Well, what position does that occupy? This is the position row 1, column 1. So what I'm going to do is I'm going to take row 1 and I'm going to multiply with column 1. All right, let's go. Let me get rid of all this. Okay, so I'm going to take row 1 and multiply with column 1. Now, what I do here is I multiply the respective terms and I add them. For example, I multiply the first with the first. So negative 2 times 2, okay? Plus, now I multiply the second with the second, 0 times negative 1. Now I multiply the third with the third. So plus 3 times 9. Okay, what does that give me? That gives me -4 plus 9 times 3 is 27. That will be 23. Now, the next one, let's get rid of these. Okay, so the next one here, in this space. All right, now this is row 1, column 2. So I'm going to multiply row 1 with column 2. Okay, so what are we going to get there? Well, the first with the first, -2 times 0, plus the second with the second, 0 times 2, plus the third with the third, 3 times 3. That gives you 0, 0, 9. So that's going to be a 9. Now, next one. We're here. Okay? Well, what position is that? That's row 2, column 1. So, all right, let's do row 2, column 1. Here's my row 2. Here's my column 1. All right, I'm going to multiply the first with the first. 5 times 2, plus the second with the second, -7 times -1, plus the third with the third, 1 times 9. What does that give me? 10 plus 7 plus 9, 26. Finally, this last one. Okay, what position is that? Row 2, column 2. So I'm going to do row 2, column 2. The first with the first, 5 times 0. The second with the second, -7 times 2. And I'm going to add these. Plus the third with the third is -11. All right, so that's how we do that one. And that is your answer right here. This is the answer. Okay? All right, now, it says to find AB and BA if possible. So now this was AB. All right, well, can we also do BA? Let's see, sometimes it's possible, sometimes it's not. Well, to do BA, what are the dimensions of B? It's 3 by 2, and A is a 2 by 3. Yeah, that works, and I'm gonna have a 3 by 3. All right, so let me write the matrices in the same order first of all. So 2, -1, 9, this is B, 0, 2, 3, times A, -2, 0, 3, 5, -7, 1. And the result is going to be a 3 by 3. All right, so we're going to do the same process. First column, first row, and so on. So this position here, this is column 1, row 1. So I multiply column 1 with row 1. I'm sorry. It's row 1, column 1. So I'm going to multiply row 1 with column 1. So 2 times -2 plus 0 times 5. This is -4. All right, now this one. This is row 1, column 2. So 2 times 0 plus 0 times 0. This one, row 1, column 3. 2 times 3 plus 0 times 3. Okay, next, here. Now, this is row 2, column 1. So it's going to be negative 1 times negative 2 plus 2 times 5. And that'll get me a 12. Next one. Here, it's row 2, column 2. So negative 1 times 0 plus 2 times negative 7. That's a negative 14. Next, row 2, column 3. Negative 1 times 3 plus 2 times 1. Okay, negative 1 times 3 plus 2 times 1, right? So that's going to be negative 1. All right, now, last row, column 1. 9 times negative 2 plus 3 times 5. That's negative 18 plus 15 is negative 3. All right, the next one. 9 times negative 7 plus, it's 9 times 0 plus 1 time negative 7. Negative, this is 3 times negative 7, so negative 21. And finally, 9 times 3 plus 3 times 1, 30. All right? Yes, it does take long. It takes a little bit longer when I write out the steps here. Do you have to write out the steps? Can you do it mentally? If you can, it's absolutely fine with me. All right, so let's go here. Again, it says find AB and BA. So let's see, A times B. So A is a 1 by 3, if we wanted to do AB. And B is a 3 by 1, right? So yes, this is possible, and the result will be a 1 by 1. So let's do that. Let's find AB. It's negative 2, 1, 3, 4, negative 6, 5. Now, I'm just going to get a 1 by 1, right? That's just one number. So what happens? Negative 2 times 4 plus 1 times negative 6 plus 3 times 5 gives you a 1. So that's it. That's just a 1 by 1. It's a number. Well, what about BA? BA, so what's B? It's 3 by 1. And A is a 1 by 3. It works, and we're going to get a 3 by 3. Oh my gosh, how do you get a 3 by 3 out of these? Well, let's see. This is B times A. And how on earth is that going to turn into a 3 by 3? All right, so here, this is the first row, the first column. Well, look at that. First row, first column. That's a negative 8. Okay? Well, what about the next one? First row, second column. That's just a 4. Well, what about the next one? First row, third column. That's just a 12. Okay, moving on. Here. Second row, first column, 12. Second row, second column. Second row, third column. Isn't that fun? Okay, lastly, third row, first column, negative 10. Third row, second column. Third row, third column. All right? Okay, so what have we learned? Look at this one. A times B gave me this matrix. B times A gave me that matrix. So multiplication is not commutative. In matrices. It is associative, so if I wanted to multiply 3 of them, I could do A times B first, then C, or in the other order. The associative property of scalar multiplication works, so if you had to multiply a scalar times A times B, you could do it in any order. Left distributive property will work, so if you have C times A plus B, you could do CA, CB, or you could do this way, CA, CB. All right. We've sort of hit on this before, and it's back. We hit it in chapter 0.6. The identity matrix has the symbol I, and its to matrices what the number 1 is in multiplying regular numbers, right? So any number multiplied by 1 is itself. Well, any matrix multiplied by the identity matrix is the same matrix back. All right, so that's what it is. It's like multiplying something by 1. Well, what does the identity matrix look like? The main diagonal are 1s, everything else are 0s. That's what an identity matrix is. All right, that's going to come in handy in a little bit. So, one thing to note, that A times a matrix is A, there is a typo here. Okay, so A times a matrix is the matrix itself. Also, the matrix I times a matrix is A. So that's like the only case where the commutative property holds. Okay. So let's talk about inverses. Well, what is the multiplicative inverse of a number? This is when you multiply, what can you multiply a number by to get 1? Well, for a number A, it's 1 over A, right? A times 1 over A gives you 1. Well, the multiplicative inverse here is the inverse matrix for matrices. So, you have a number 5. What do you multiply that by to get 1? Well, you would have to multiply it by 1 over 5 to get 1. Okay, you have a matrix A. What do I multiply it by in order to get the identity matrix? Well, if I have a matrix A, then I have to multiply it by A inverse in order to get the identity matrix. Okay? So the notation looks like this. A times A inverse, or A inverse times A, gives you the identity matrix. Okay? All right. So let's talk about inverses. First off, suppose you're walking down the street and you see 2 matrices, and you and your friend get in an argument over whether or not those 2 matrices are inverses. Well, how do you put the argument to rest? Well, here's what you do. You have a matrix A, you have a matrix B. To check if they're matrices, we have to do 2 things. Multiply A times B, then multiply B times A. If you get the identity matrix both times, then they're inverses. Okay? Sometimes there are those rebel matrices out there that have no inverses. We call those singular matrices. Okay? All right. So let's see if A and B are inverse matrices. All right. Let's multiply 5, 6, 4, 5 times 5, negative 6, negative 4, 5. So this is a 2 by 2. This is a 2 by 2. The answer is going to be a 2 by 2. All right? Now, let's do the first row, first column. So I'm going to get 5 times 5 plus 6 times negative 4. All right, and that's going to give me a 1. First row, second column, 5 times negative 6 plus 6 times 5 is 0. It's looking good so far. Second row, first column, 4 times 5 plus 5 times negative 4. Hey, that looks like a 0. Second row, second column, gives me a 1. Oh my gosh, this is the identity matrix. How awesome. So far, so good. Now, let me do B times A. So this was A times B. Now let's do B times A. Well, that's going to be 5, negative 6, negative 4, 5, 5, 6, 4, 5. Okay? All right. So first row, first column, I get a 5 times 5 plus negative 6 times 4, that gives me a 1. First row, second column, 5 times 6 plus negative 6 times 5, that gives me a 0. Then on the bottom, I get negative 4 times 5 plus 4 times 5, that gives me a 0. Lastly, negative 4 times 6 plus 5 times 5, I get a 1. Oh my gosh, I got an identity matrix here. I get an identity matrix there. These two are inverses. Okay? All right, so how would we find an inverse though? Okay, how would we find an inverse of an identity matrix? Well, of any matrix. All right, we're going to start with the 2 by 2s. It is so much fun to do these. Okay, so you've got a 2 by 2 matrix here. Okay, you know what you do. Here it is. So first, we have to find what we call the determinant. Okay, I have it here. All right, determinant has its own symbol. Okay, it's the bars. So whenever you put A with the bars, you're saying the determinant of A. Okay, you could also, if you have a matrix that looks like this, A, B, C, D, this is how we denote matrices, with a bracket. However, if you wrote A, B, C, D, not with the brackets, but with the bars, you're saying, okay, the determinant of this matrix. So here's how we find determinant. You multiply the main diagonal, A times D, minus, now you multiply the other diagonal, C times B, and that's your determinant. Okay? Now, well, how would you find the inverse then? Once you find the determinant, okay, it's 1 over the determinant, and what you do is you switch the places of that main diagonal, so A and D become D and A. The other ones stay where they are, but their signs switch. Okay, I admit what I just said seems very, very complex. But you know what? Let's do one and you'll see how much fun it is. I'm a little anxious to do this. Okay, let's go. You know what I'm going to do, actually, is I'm going to do B first. So let's do B first. All right, so first, I find the determinant of A, and the determinant of A is going to be 6 times negative 2 minus negative 4 times 4. All right, and that'll be negative 12 plus 16, 4. So the determinant is always going to be a number. It could be positive or negative, it doesn't matter, but it's always a number. So that's the determinant. Now, what's A inverse? A inverse is 1 over this determinant times. Now, the main diagonal, let me just erase some of these. The main diagonal will just switch places. So negative 2 and negative 6 will switch, and it'll be 6 here and negative 2 there. The other two stay where they are, but they switch sign. Okay, that's all. Now we need to distribute, right? So everybody gets a 1 over 4, meaning this is 6 over 4, negative 4 over 4, 4 over 4, negative 2 over 4. How much of these intermediate steps do you have to do? Well, you could totally skip that last one. All right, I'm just showing it to you for illustration. So this is 3 over 2, negative 1, 1, negative a half. And look at that. That's your inverse matrix. All right. So now let's do the other one. The one before. Okay, so let's find the determinant. This time I'm going to refer to the determinant like this. The two notations are interchangeable. So it's going to be negative 5 times negative 8 minus 4 times 10. Okay, this is 0. All right, so we got a 0 for the determinant. Well, what does that mean? To find the inverse, remember how we said we had to do 1 over the determinant times the other stuff? Well, 1 over 0 can't work. So when you get a determinant of 0, we say this is singular, which means it has no inverse. Okay? Best case scenario. All right. Now, the best one of all, determinant of a 3 by 3. Okay? Here we go. All right, so here's a quick way to do it. There is one way here, which I'm not going to go over, but look at the quick way. So reproduce the first and second columns to the right of the matrix. Find the products of the respective diagonals. Add the products going left to right. Subtract the products right to left. Okay? What does that mean? Look. We take these two rows, columns, and we just reproduce them here. Okay? Now, I multiply and I add all the numbers along the rows. So for example, along each diagonal, right? I have an A times an E times an I, a B times an F times a G. So I add all of the products along the red diagonals, and I subtract all of the products along the black diagonals. All right, let's just do an example. Here we go. First, reproduce the two columns. 3, negative 2, 1. 1, negative 1, 2. Now, we're going to draw arrows, or just lines. 1, 2, 3. Okay? Let's multiply everything. Let's multiply the numbers on each of the diagonals. So 3 times negative 1 times 5 plus 1 times 4 times 1 plus 0 times negative 2 times 2. Now, I'm going to go in the other direction. 1, 2, 3. Now, each of these green ones are going to get a minus sign. So minus 1 times negative 1 times 0, minus 2 times 4 times 3, minus 5 times negative 2 times 1. Okay, now watch. What are we going to get here? Negative 15 plus 4 plus 0 minus 0 minus 24 plus 10. All right, you add all these up, you get negative 25. What on earth does that mean? The determinant of A is negative 25. And look at that. Oh my God. There can't be much in the world that brings you greater satisfaction than doing this. I'm sorry. Okay? All right. So here's the problem set, which we'll be working on tomorrow. If you have any questions on any of this, write them down. I know it's all brand new stuff. Write them down, and we might be able to dedicate some time at the very beginning of class tomorrow to ask questions. All right? Thanks, everybody.